Hello, everyone. Welcome to our presentation about the Rascal Wedge. I'm Fatima Chowdhury, and my teammates are Matthew Colpitts, Mason Yamamoto, Saksham Shrestha, and Salvador Maldonado. In our agenda today, we're going to be discussing the background of our industry project, the Rascal Wedge, the objective of our experimentation, the setbacks and solutions we came up with through this entire process, the methodology of our experimentation, and the analysis from our experimentation and conclusion. For the background, the Rascal Wedge was introduced to us as an industry product that we were doing compressive strength analysis on a, an aluminum wedge. The Rascal Wedge was an innovative product designed for firefighters to answer a simple question for forcible entry during a fire situation. The Rascal Wedge has the similar weight to a wooden wedge with more functionality added to it, as it can be used as a multi-tool during fire situation, and it can go up in the firefighter's headgear to assist them in the fire situations. For the process, we first devised a plan with the advice from our professor, Carl Hoover, and our industry liaison, Greg Rios. We came up with a plan to test different sites on the Rascal Wedge to determine failure in accordance with the force applied to the Rascal Wedge. Then we created a preliminary finite element analysis simulation where we found out what possible forces could create distortion in the fixtures themselves, and then we executed the same procedure in the lab using load frames.
For the FE analysis, the team created a 3D model of the Rascal wedge in SolidWorks, ensuring accurate geometry representation. For the meshing of the model, it was meshed with a curvature-based mesh, which creates more elements in higher curvature areas automatically without need for mesh control. So these fine elements were used to capture detailed stress and deflection behaviors of the wedge. We also put boundary conditions, which are like fixed constraints applied to the base of the wedge to like simulate its attachment to a surface. And for loading, a uniform pressure load was applied on top surface to simulate typical uses conditions during a firefighting scenario. For von Mises stress analysis, the results were that the analysis revealed that the bond recess stress was highest at the tip of the wedge, indicating a potential failure point. And the implications were that uh, this is like a crucial piece of information for design improvements to reinforce this area and prevent failure under load. And for deflection analysis, it showed that the maximum deflection occurred near the right edge of the hypotenuse of the wedge. So in visualization, the deflection was quite significant enough to be visibly observed. And as in conclusion, we identified the critical points of failure and deformation in the Rascal wedge. And it also provided us valuable insights on how the wedge could deform when carrying out the actual experiment with the load frame in the lab. Now, the main objective of this test is to firstly make a social impact by assisting the firefighters with providing a multifunctional tool with various functionalities during a firefighting situation. The second objective is to determine the compressive strength of two products, the Rascal wedge and the conventionally used wooden wedge. And The third objective is to compare the two wedges and find out by what factor the aluminum wedge is stronger than the wooden wedge.
Okay, our setbacks and solutions. So we had some minor and major setbacks. Our minor ones was conflicts of schedule. We're all pretty busy during the day, so we had to keep in contact with each other, see what we can do with that. And then we also needed training for equipment that we had to use, our lack of proper safety training, and obtaining the test results or test subjects. Some of the major setbacks was issues with the workshop, some problems with their budget, incorporating our upper and lower fixtures because of design problems. So some of the solutions that we did was establish weekly meetings with each other, receive operating instructions from our professor Carl Hoover, attend these safety training classes, and we also asked the company if we could have wedges. So we got 6 wooden wedges and 6 aluminum wedges. And then for major problems, we fixed units and added needed files. We used our own money for the project, and we designed upper and lower fixtures.
All right, so now for our methodology. Okay, so first, the equipment used for the project. The most important tool was the hydraulic-based load frame with a 100 kilonewton load capacity and a precise error tolerance of 0.27%. On the other hand, the data collection was done through the Bluetooth software, which was already installed on the lab computers. On top of that, we used MATLAB and Excel to arrange the data into graphs and to obtain crucial information. The test subject for our project were 2 different types of wedges: the conventional wooden wedge and the new product, the Rascal wedge, made of aluminum 6005 T61. This is a product designed by Utul company, equipment company. In order to carry out the project, we needed to design 2 different fixtures. This consisted of 2 parts, a lower one and an upper one. They both have different jobs. While the lower one is in charge of keeping the wedge in place with its triangular design and walls on the side, the upper one is in charge of evenly applying force at different points. The material for both of them is steel. This is to ensure that the fixtures don't deform before the premise of the wedge. Okay, and lastly, the force application. We just needed to define the different points in which the force was going to be applied. These were defined by our advisor, Greg, with the idea of point 1 and 2 being practical applications of the wedge, mainly when it's used to force a door open, and 3 because it's likely the weakest point of the design.
This is our results analysis. So this is our load versus extension data. On the left, we have the wooden wedges, and on the right, we have the aluminum wedges. So the wooden wedges, as you can see, have a plot where they compress almost indefinitely. So there isn't a yield point, whereas at the aluminum, there is yield because it's hollow as opposed to the solid wooden wedge. So as you can see, though, the aluminum wedges are overall stronger. Even at the weakest point, which was site 3, the aluminum wedge still has a higher slope to the curve, meaning it is overall stronger, even though the peak is lower than the wooden wedge. So those numbers on the screen don't really mean a whole lot, but these are the pictures of what the tests actually do to the wedges. So as you can see, the wooden wedges only really dent. They don't have a lot of deformation, but you can still see that there's an impact. Whereas the aluminum wedges not only yield, but almost snap in the way that they break. So this is just a way of showing how that 4 millimeter deformation actually looks on a wedge. So maximum force, as you can see here, was higher for the aluminum on most fronts. The only front where it wasn't was site 3, which was the weakest possible point on the wedge. And that was more just to see what would happen if we did this, what type of thing would we see, what type of behavior would we see if this happened. But the aluminum at sites 1 and 2 is much stronger and has a much higher maximum force before it yields.
Okay, so our conclusion. So what we concluded was that the aluminum wedge was stronger than the wooden wedges at all the test sites. And the test site that was the strongest on the aluminum was site 2, and the weakest was test site 3, as predicted. So some of the key takeaways that we had was the aluminum wedge was strongest at site 2 and weakest at site 3. The aluminum wedge is stronger than the wooden wedge, and the Rascal wedge can add functionality without removing reliability. And each team member now has proper security and load frame training if additional tests are necessary.
So just at the end, we'd like to thank our advisors, Dr. Weber and Greg. Greg was a huge help throughout the whole process. We had no idea really what we were doing. And his product was a really cool thing to work with and test. And he was a great guiding force throughout this. As was Dr. Hoover. That was a lot of setbacks in this, a lot of issues, and he was there for us at every step. And we just really appreciate the help of both of them. So thank you for that.